Okay, now we're going to take a look at a couple of examples. I want to talk about the process, though. In solving related rates problems, we're first going to find an equation that relates the quantities of interest. In our the previous video, I gave some simple illustrations of that, and we'll see some more like that in the coming problems. Again, this is important that you understand these geometric relationships, areas, volumes, similar shapes, and the Pythagorean theorem, as well as the right triangle of geometry. And there could be other models that come through the sciences or through business models and economics and such. When we're doing this process, if it's not clear, you should clearly identify any variables you use. Either typically if you have a geometry type problem, you can label the diagram and indicate your variable quantities there, or you can write in a brief statement what they represent. So you shouldn't assume that I know what any variables represent. The one exception we will see is that we will universally use the letter T to represent time, and so that will always be the case. There's a lot of times our quantities that we deal with are changing with respect to time. Once we have the equation, our second step will be essentially the calculus step. That's where we're going to find the derivative. We're going to implicitly differentiate both sides of the equation with respect to time, and that will give us our related rates equation. So we're going to find that equation first, that related rates equation. Then we can use that related rates equation to find the value of any unknown rate, provided we are given specific information. So here's our first example, which is very simple. Suppose that we take a pebble and we toss that pebble into the pond. What's going to happen? We can visualize it as forming concentric circular ripples, right, of water that emanates from that center location. If the outermost ripple is increasing at a constant rate of 2 feet per second, when the radius is 4 feet, at what rate is the total area of the disturbed water changing? Well, it helps to first of all draw a little diagram. If we're looking above from where we toss the stone into the water, or pebble into the water, it's going to have these ripples that emanate out, and the outermost ripple at some time might look like this. And then we can think of the important parameter or dimension, if you will, for this circle would be its radius. If we think about from this point where the pebble hit the water to the outermost ripple, let's just call that R for radius. Okay, and there's what I mean about declaring the variable. I'm declaring R to represent that length, and R is increasing as this water ripple moves further and further away, and the circle gets bigger and bigger. Again, there's the outermost ripple that we're looking at here. And so the other quantity of interest is we're interested in the rate that the total area of the disturbed water is changing. So let's let A equal the area of the disturbed water. That's the water within the circle. And what I like to do is in these rates, related rates problems, we are usually given at least one rate and then asked to find another rate. So when I say given, I'm talking about a given rate, and then which rate are we asked to find. The given rate in this problem, if you look at it, the outermost ripple is increasing at a constant rate of 2 feet per second. Right? So that's the rate that we're given. And what does that relate to? What exactly is that? What is a rate or a rate of change? And the answer is the rate of change is a derivative. And so if you remember, we talked about the derivative as a rate of change. What function are we differentiating here? What function are we finding the derivative of when we talk about the outermost ripples increasing at a constant rate of 2 feet per second? Well, that's the rate of change of R, right, this radius, with respect to what? Time per second, right? Feet per time. And so the given rate of change is the derivative of r with respect to time. And we know that's going to be 2 feet per second. It is important to note that that's a positive 2 feet per second because the value of r is increasing as time progresses. And we think about a graph of the function of the time as the horizontal axis in our radius here, right? Then what we're going to see is that over time this is increasing. The radius is increasing, and so at any point, if we find the derivative, it's going to be positive. So it will be important to make sure that we indicate whether these given rates are positive or negative. What are we asked to find? When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Well, what is that? That's the derivative of what? The area of disturbed water with respect to time. That's what we're supposed to find. And I'll go ahead and write that we're supposed to find it when what? The radius is 4 feet. The radius r is 4 feet. Okay. Now it's real important what we're going to do. That's just setting up the information we have. So our first step, if you remember, is to find an equation that relates these quantities of interest. What are the quantities of interest? The disturbed area A and the radius r of the circle. Well, I hope right away that you understand that that equation is simply comes from the fact that we know the equation of the area of a circle. The area of it is pi times r squared. Keep in mind, though, both A and r are variable with respect to time. They are not constants. So r equal 4 feet. Should we plug in r equal 4 feet now at this point before we do anything else? And the answer is no. Remember, you always want to evaluate the derivative before you plug any values in. Otherwise, if you're plugging in first, you get a constant. You take the derivative of any constant, you get 0. Right? So we need to go ahead and take the derivative first, and that's going to give us our related rates equation. And so that's that second step here. We're going to implicitly differentiate both sides with respect to time. So essentially this is implicit differentiation, but this side's real easy. What's the derivative with respect to time of the area? Well, that is simply dA dt, the rate of change of area with respect to time, which, hey, by the way, is what we're looking for. Over here, r is certainly a variable with respect to time, but pi is not. Pi is a constant, so pi can come out, and we take the derivative of r squared. How do we take the derivative of r squared? Well, be careful. It is the chain rule. Yeah, it's the chain rule. The outer function is r squared, right? The squaring function. The inner function is just r. And so if I take the derivative of r squared by the chain rule, it's what? Derivative of r squared is 2r. That's the derivative of the outer function evaluated at the inner. Times the derivative of the inner function. What's the derivative of the inner function? Well, that's just the rate of change of r with respect to time, dr dt. So this right here, again, is the chain rule. And so now we have our related rates equation. And now we can answer the question, right? So in fact, we know that the dA dt, when what r is equal to 4 feet, is what? Well, let's plug in the parts. We got pi, we got 2, r we said was what? 4, and dr dt is what? Dr dt is that given rate up here, 2 feet per second. And so I can now evaluate this, and we get pi times all this. This is what? 16 pi. Now, it is important to give units. What would the units of dA dt be? What would the units be? 16 pi what? Well, remember, A is area, right, which is measured in this case, obviously, in what? Square feet. per what? Unit time. So it should be square feet per second. Those are the time units. And we could get that, of course, if you look at this here. Remember, the value of R is in feet, right? So this will be 4 feet. And dr dt is in what? Feet per second. So what is feet times feet per second? It's going to be square feet per second. So we could also get it that way. Okay, we're going to look at one more example, a little bit more involved, and then let's take a break. So here we have a trough. I don't know if you all know what a trough is, but might be something that we use to give water to our animals out in the pasture, out in the field. This is a trough, and it's got a triangular cross-sectional design. It's 12 feet long, 4 feet across the top, and the ends, again, are triangles, as we said, with an altitude of 3 feet. So it's a constant cross-sectional area going through there. So at the instant the water level is 2 feet deep, the water is draining from the trough at a rate of 16 cubic feet per minute. How fast is the water height in the trough changing at this instant? Okay. Well, what I'd like to do is, first of all, I want to draw a little diagram that shows if I'm looking towards the trough from this end, I'm going to see this triangle. I just want to look from that end and see what I have. If I know that the width across the top there is 4 feet, so from here to here is going to be 4 feet. And then the altitude, the height of this triangle, is 3 feet. So if I just wanted to find the volume of the whole trough, how would I do that? Since it's a constant cross-sectional area, I find the area of the triangle, and then I multiply it by the length here, which is 12 feet. Of course, the area of the triangle is 1/2 base times height, so that would be 1/2 4 times 3, or 1/2 times 12, which is 6 square feet, times 12 feet would give me a total of 72 square feet. That would be the, cubic feet. That would be the volume of this trough. Of course, the volume of the trough is not changing. What is changing? Well, the level of water in the trough. So if I was looking from this end and this end was maybe transparent, I could look through there at some point and I would see the water. Let's draw a little thing of water. So the water would level would be up to here. So what would be the volume of the water at this point in time? Well, as the water is draining, its height is going down, right? As the water drains, its height's going down. So what is its height? Well, it's variable. I want to give a quantity to that. I'm going to call that height A. Now I know it says the instant the water level is 2 feet deep, but remember, the water's changing. It's not a constant at 2 feet. We need to find the related rates equation first before we plug in that 2 feet deep. When we do, of course, at that instant, A would be equal to 2. But we don't want to let A be 2 now, because then when I take the derivative, again, the derivative of constants, not what I'm looking for. This A is changing with respect to time. If you think about it, A is getting smaller as time progresses. The other variable quantity is, I can think of the distance across the top of the water. You can see as it drains down that this distance going across the top of the water is getting smaller and smaller. We call that V. So these two quantities are changing as time progresses. Both are getting smaller, and yet there's one more variable of an instant of importance. We're asked to find how fast the water height in the trough is changing. So the water height would be this A that's changing, but we are given that the water is draining from the trough at the instant it's 2 feet deep at a rate of 16 cubic feet per minute. So what is that rate of change? Well, that represents the volume of the water in the trough. So we're going to let V equal that volume of water in the trough. Now, what are our given what's our given rate of change, and which rate of change are we asked to find? Well, the given rate of change, we just said, was that the water is draining from the trough at a rate of 16 cubic feet per minute. So that's the rate of change of V, the volume of water in the tank, with respect to time. That's the derivative dV dt. And now, 16 cubic feet per minute, is it positive or negative 16 cubic feet per minute? Give you a second to think about that. Should it be positive or negative? Read the problem statement very carefully. So I hope you'll see that this rate of change has to be negative. And that's because the water is draining out of the tank. The volume of water in the trough is going down. So again, if I were to graph the volume of water in the tank versus time, we're going to see that it's going down over time. We don't know that it's going down necessarily linearly. We just know the instant it's 2 feet deep, the rate of change is this 16 cubic feet per minute. But it's got to be negative. If you think about it, at any point in time, if I find the derivative, which is the slope of the graph at that point, we're going to find a tangent line that's got a negative slope. The derivative is going to be negative. Okay. But again, the water's draining out of the tank, the volume is going down, so it makes sense that dV dt is negative. And you're going to have to make sure that negative's on there. Okay. Now, what are we asked to find? How fast is the water height in the trough changing? Well, that's the rate of change of A with respect to time. And we want to find that the instant when what? When the height A is equal to 2 feet. Okay, so where does our equation come from this time? Well, we just talked about it a minute ago. It's the volume of water in the trough, right? That volume is equal to what? The area of water here times the length of the trough, 12 feet. So what's the area of the water here? It's 1/2 base times height. Well, the base would be B, and the height would be A. So it's 1/2 A times B times the length 12, which is, of course, 12 times 1/2, 6AB. Now, one thing that's interesting about this equation is it has the volume in terms of both A and B. And these two quantities, A and B, are changing, right? They're both getting smaller as the water drains out of the tank and this water level goes down. B is getting smaller and A is getting smaller. But if you look at the information that we are given and what we're asked to find, you'll see that one of the variables is kind of not mentioned, or sort of excluded, if you will. Not mentioned directly, and of course that is the quantity B. We're told how V is changing, and then we're asked to find how A is changing. So when I look at my equation, it would be nice if I can just get V and A related to one another. Is there any way to do that? If there is, we should try and do that. And the answer is yes, we can. If we look at this picture, there is a geometric relationship that's very important in these types of problems that we're going to use, and that is that the trough itself and the water form triangles that are similar. And we know that similar triangles have their side lengths in proportion to one another. And therefore, if I look at the top of the water, the length of the top of the water across the top, to its depth or height, which would be B is to A, well, that ratio is the same as the trough's distance across the top to its height, which is 4 is to 3. So B is to A as 4 is to 3. But this is a relationship now that I can solve for B by simply multiplying both sides by A. I get B is equal to 4/3 times A. And so what I want to do is I'll take this quantity for B and substitute it back in here, and my equation relating my variables will just be in terms of V and A. So V is what? 6A, and B is what? 4/3 A. So I get V is 3 goes into 6 twice, 2 times 4 is 8, A times A is A squared. There's my equation now just in terms of my variables of interest. So now the calculus comes into play. I take the derivative with respect to time of both sides. The derivative with respect to time of v is just dv dt. Here, 8 is a constant multiple. We can pull that out. What's the derivative of a squared with respect to time? Well, chain rule. Very similar to what we did in the last problem. 2a is the derivative of the outer function, evaluate the inner, times the derivative of the inner function, dA dt. So remember, a is a function of t, and we're taking the derivative with respect to t. So I've got a inside the squaring function. I have to use chain rule. 2 times 8 is 16. Okay. And there's my related rates equation again. And you have to get this first before you do any plugging in of any quantities. Now, we're asked to find dA dt the instant when a is 2 feet. Now I can plug in. Don't plug in a is 2 feet now. If you do it up here, you're going to not get the right result. Because a is not a constant, it's changing. A is getting smaller again as time progresses. So let's take a look at this now. If I want to find the rate of change of volume with respect to time at the instant that a is 2 feet, what do we get here? Well, I'm just going to plug in here 16. A is what? 2 feet. Right. And what's dA dt? Well, that's that given rate of change, right? I'm sorry, we're looking for dA dt. I'm sorry. dA dt, and it's dV dt that we know. Sorry, so dV dt we do know is negative 16 cubic feet per minute. So this quantity here is negative 16 cubic feet per minute. So I've got negative 16 equals 16 times 2, which is 32 dA dt. Can you solve for dA dt? Yeah, divide both sides by 32, and 16 divided by 32 turns out to be 1/2. And so notice I get dA dt, the rate of change we're looking for, is negative 1/2. What would the units be in this case? What would the units be in this case? dA dt. A is measured in what? Units of feet. T is measured in units of time in seconds. And so this should be feet per second. Feet per second. The rate of change of the height with respect to time is in feet per second. Now, I want you to notice something real important, and that is the fact that this rate of change is negative. Is that good or bad? Well, it's good, because what should be happening as time progresses, A is getting smaller. So dA dt should be negative, right? And you know what's going to happen if you don't originally notice that dVt is negative. If you keep that as being positive, you bring that positive all the way down, what's going to happen down here is you'll get dA dt is positive, which would be not true if you think about the problem. So always when you get done to the final answer here, see if your answer makes sense. You can tell, if a quantity's increasing, the rate of change should be positive. If it's decreasing, the rate of change should be negative. Okay, we'll stop the video here, and then we will look at some more examples in the next videos.